Hello, Accelerated Chemistry students. This is Mr. Spurk, and this is your Chapter 9, Section 1 notes all over naming ions. So the first thing we want to talk about is, do you speak chemistry? And the answer to that is yes, of course you speak chemistry. So if we look at food labels, now that we're talking about ions, we see how prevalent ions truly are in the foods that we eat. So if we look at the food label on the left, you can see that the active ingredient is actually sodium fluoride, which we know is NaF. And then if we look at the food label on the right, we can see another ion that might seem a little familiar since you guys have been studying that list of 60 ions as calcium phosphate. So the next thing we're going to talk about is monatomic ions. Ionic compounds consist of a positive metal ion and a negative nonmetal ion combined in a proportion such that their charges add up to a net charge of 0. So if we try to break down the ionic compound sodium chloride, we know that sodium, Na, carries a +1 charge, and we know that chlorine carries a 1 minus charge. So when we add together +1 and -1, we get an overall net charge of 0. And that's what we're looking for from monatomic ionic compounds. Monatomic ions consist of a single atom with a positive or negative charge resulting from the loss or gain of one or more valence electrons. So a monatomic ion is our Na+, and another one is Cl-. Next thing we need to talk about is cations. So let's recall that metallic elements typically lose valence electrons. So for example, we have groups 1a, 2a, and 3a as our metallic elements that are going to lose valence electrons to have a positive charge. The names of these cations are the name of the metal followed by the word ion. So for example, the sodium +1 would be sodium ion, Ca2+ would be our calcium cation or ion, and Al3+ would be aluminum ion or aluminum cation. Another thing on contrary to cations is anions. Nonmetals typically gain electrons, so the charge of the nonmetallic ion is negative. So to figure out the charge on these ions, we can take the group number and subtract 8. So for chlorine, it's in group 7a, so we say 7 minus 8 would give us -1, and that's true. We know that chlorine has a -1 charge. Or we can say that charge equals the number of valence electrons minus 8. They're really the same thing, so whichever way you want to remember it is really just up to your choosing. So for example, let's look at nitrogen. So nitrogen is in group 5a, and it has 5 valence electrons. So we take 5 minus 8, and we get -3. So when we can assign the -3 to the charge of the nitrogen. So the nitride ion is N3-. The names of anions start with the stem of the element name and end in IDE. So the Cl- ion, we would classify and name that as chloride. So we take the start of the metal or the element name, so that'd be CHLOR, and we cut off the ending and change it to IDE, so we have the chloride ion. So another way that I like to remember which side of the periodic table is positive and which side is negative, I think about them being losers and gainers. So over here on the left side, we have our losers because they are going to lose electrons to become positive. And over here on the right side, we have our gainers because they gain electrons and have negative charges. So another thing we need to talk about is metals that form more than one ion. So many transition metals form more than one cation with different ionic charges. So for example, we have chromium, manganese, iron, cobalt, copper, mercury, tin, and lead. And I'm actually going to be providing you all with a list of some common transition metals and their different forms that they take. So we'll be adding more ions to our list to study up on. And the charges of these cations must be determined from the number of electrons lost. So for example, we have Fe2 plus, which means that iron cation has lost 2 electrons to be 2 plus. And we also have iron 3 plus, which means that particular ion or element has lost 3 electrons to give us iron 3 plus. The stock system helps us name these ions with more than one common ionic charge. And the stock system places a Roman numeral in parentheses after the name of the element to indicate the numerical value of the charge. So for example, like we just said, we had iron 2 plus, Fe2 plus, and we read that as iron 2 ion. So when writing it out, we would spell out the word iron, put a parenthesis, and then put a Roman numeral 2 to tell us that that is the iron 2 ion, Fe2 plus. An older method for naming these cations uses a root word with different suffixes at the end of the word. So for example, we have ferrum, which is Latin for iron. So Ferr is the root name for iron. And the suffix ous is used to name the cation with the lower of the 2 ionic charges, and the suffix ic is used with the higher of the 2 charges. So Fe2 plus would be the ferrous ion because it's the cation with the lower of the 2 ionic charges, and Fe3 plus has the higher of the 2 charges, so we change the name to the ferric ion. A major disadvantage of using classical names for ions is that they do not actually tell us the charge on the ion. So we could say cuprous ion, which would be copper 1 or copper 2, but that actually doesn't tell us what charge is on that ion. So cupric, we know, has a higher charge than cuprous, but we don't know what the charge on that ion actually is, which is why we use the stock system with the Roman numerals to indicate the charge that accompanies the metal. A few transition metals have only one ionic charge, and the names of these cations do not have a Roman numeral. So the exceptions are Ag+, which is silver, cadmium 2+, and zinc 2+. So when we write these ion names, we just say silver ion, cadmium ion, and zinc ion. So let's go through a few examples. So we have potassium, which we know is in group 1A and has a +1 charge. So we know that the symbol for potassium is K. That's a terrible looking K, but that's all right. We can go back through and try again. So when we assign this, we assign K +1, and we know that the name of that is going to be the potassium ion because it is a cation. So our next example is lead, which we know the symbol is Pb, and it tells us that we have lost 4 electrons. So that means that our charge is going to be 4+. So Pb4+ is going to be written as lead with the Roman numeral 4, and a 4 is IV. Then we have sulfur. We know that sulfur is in group 16, so we can say 6, because it's in group 6A, 6 minus 8 equals -2, which gives us the charge on the sulfur ion. So the symbol for sulfur is S minus 2. And we would classify this one as the sulfide ion because it is an anion. So now we need to talk about all those polyatomic ions that you've been studying. So how do polyatomic ions differ from monatomic ions, and how are they similar? Unlike a monatomic ion, a polyatomic ion is composed of more than one atom. But like a monatomic ion, a polyatomic ion behaves as a unit and carries a charge altogether. So let's consider the sulfate ion. It consists of 1 sulfur and 4 oxygen atoms, so SO4, and together this unit carries a 2- charge. So like monatomic ions, the polyatomic ions work together. They are one unit and they carry one charge. Typically, their names end in ITE or ATE. Sometimes two or three elements combine in different ratios to form these different polyatomic ions, such as SO3 2-, which we know as the sulfite ion, and SO4 2-, which we know as the sulfate ion. And note that the number of oxygen atoms and the endings on each name. You should be able to eventually recognize a pattern, and hopefully you've already learned these names and figured out the patterns. The charge is the same on each polyatomic ion in a pair for which there is both an ITE and an ATE ion ending. The ITE ending indicates one less oxygen atom than the ATE ending. However, the ending does not tell you the number of oxygen atoms in the ion. For example, the nitrite ion, which we know as NO2-, and the sulfite ion, which is SO3-. So although these ion names both have the same ITE ending, that ending does not tell us how many oxygen atoms are present in the polyatomic ion. When the formula for a polyatomic ion begins with H, you can think of the H as representing a hydrogen ion, which is H+, combined with another polyatomic ion. So for example, we have the bicarbonate ion, which is HCO3-, is a combination of H+ and CO3 2-. And so note that the charge on the new ion is the algebraic sum of the ionic charges of the two component ions. So we have H plus 1 and CO3 2-. So we add plus 1 and 2-, and we end up with an overall net charge of -1, which is why HCO3 is a 1- ion. Most polyatomic ions are very prevalent in our lives. HCO3, HPO4 2-, and H2PO4 2- are dissolved in our blood and are critical to our health. And HCO3- is basically just Alka-Seltzer tablets, which we've used in the lab before, and those help us relieve an upset stomach. But in contrast, we also have polyatomic ions such as the cyanide ion, which is extremely poisonous because it blocks the cell's means of producing any energy. So in review, when the metals in groups 1A, 2A, and 3A lose electrons, they form cations with positive charges equal to their group number. The charge of any ion of a group A nonmetal is determined by subtracting 8 from the group number. The charges of the cations of most transition metal ions must be determined from the number of electrons lost. And unlike a monatomic ion, a polyatomic ion is composed of more than one atom. But like a monatomic ion, a polyatomic ion behaves as a unit and carries a charge. Good news, we've finally reached the end of Chapter 9, Section 1 notes. And as always, the information on these slides has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook, Resources CD, pearsonchem.com. Thank you so much and have a good night.